Hello everyone, my name is Fuminori Shibasaki. I'm a first-year master's student and a member of Fujishiro lab at Keio University. In this video, I will present topological analysis and approximate identification of leading lines in artworks based on discrete Morse theory. Leading line is a pathway within a composition for observers, and painters and photographers often incorporate this line into their work to guide observers' attention and emphasize the main subject. These leading lines are not always delineated explicitly as straight lines, but it can also be abstracted lines of sparsely arranged objects, or it can be gradations and textures of brushstrokes. It can also be expressed by human gestures, like in this painting. Identifying these leading lines can be valuable in art appreciation because it allows us to objectify the content of artwork and it helps us understand its structure. But it's sometimes difficult for people without background in art or photography education to recognize the leading line. And also artists themselves sometimes have difficulty in identifying leading lines in their own artwork because their eyes get used to it after working on the same piece for a long time. Therefore, in our study, we present an approach to approximating the identification of leading lines computationally from an input image by abstracting the gradient field of a saliency map based on discrete Morse theory, and make the system accessible to novice artists and to people who are interested in developing their art appreciation skills. And finally, we compared the output results of our approach with the eye-tracking results of average observers. In paintings like this one, artists modify contrast and precision of drawing to emphasize some areas and place those areas to effectively express leading lines. So, we first began with extracting highly attractive areas as a basis of leading lines by using saliency map. This saliency map is a low-level image feature that computes the sensors around differences in visual stimuli. Although visual attention models based on saliency have been used in various fields like ad design, media quality assessment, and analysis of medical images, such scalar features do not express the trajectory of eye movements. So, we focused on the gradient field of the saliency map, because human eyes are drawn from highly salient regions to less salient regions. This visualization of gradient field using arrow plots enabled us to depict the local feature of leading lines, but the dense arrangement of many glyphs, which tends to overlap each other, led to visual clutter and it was unsuitable in identifying comprehensive leading lines. So, as an alternative to the arrow plots, we used an abstract representation by one cells of Morse-Mel complex, also known as the extremum graph, which is simply a path from saddle points to maxima and minima that follows the locally steepest descent. The Morse-Mel complex partitions the scalar field into uniformly gradient regions by interconnecting all critical points as a graph, and is known to benefit the shape analysis of scalar fields on manifolds through segmentation. However, to visualize the leading lines that connect sparsely arranged salient areas, it is not necessary to include low saliency points in the graph. Consequently, we decided to analyze such sparse leading lines by extracting the maximum graph, a subgraph of extremum graph, which only connects the maxima and saddle points. As mentioned earlier, leading lines do not always form explicit lines. Moreover, our eye movements alternate along a path repeatedly while scanning an image, and the leading line can be identified as a central path that represents the bundle of gaze trajectories. Therefore, we believe the skeletal representation of segmented regions provided by one cells of Morse-Mel complexes closely resembles the structure of leading lines. However, detecting all critical points in the saliency map, including minor maxima, may complicate the analysis. So we set a threshold on the persistence of critical point pairs to control the level of topological detail by selectively removing minor critical points. We developed the visual analysis system on this environment by mainly utilizing the OpenCV and the TTK libraries. Currently, the saliency maps are downsized to 256 by 256 regardless of the original resolution because the number of detected critical points is restricted to a maximum of 10,000 pairs in our implementation. Deriving the Morse mole function requires less than 10 seconds, and the subsequent thresholding process can be carried out interactively on ParaView as you can see in the video here. For eye tracking, we used the Tobii Pro Spectrum eye tracking device with the Tobii Pro Labs software to monitor the eye movements of 6 students majoring in computer science. The images were presented for 10 seconds each on a full screen at a distance of 60 cm from the observers without any specific task. This is a comparison between the ideal leading line on the top left. Below that is the output results of our approach, and the rest is the actual eye tracking results of 6 average observers. You can see that our approach closely approximated the ideal leading line and shows qualitatively similar connections with the tracking results. These are the leading lines approximated in a range of artworks. In our study, we demonstrated the validity of maximum graphs derived from saliency maps for the visual analysis and approximate identification of leading lines in artistic compositions. Furthermore, we conducted a comparative study on the approximated leading lines using a variety of paintings and photographic works along with eye tracking results obtained from real observers. To the best of our knowledge, this is the first report on leading line approximation utilizing discrete Morse theory. As for future work, we aspire to conduct third-party evaluation experiments on the output results for a more quantitative comparison, since we have only demonstrated the efficacy of our approach by monitoring the gaze of average observers. Secondly, we plan to provide a good initial guess for thresholding on the persistence value by applying the elbow method to the persistence curve, so that the people without a background in art education can easily identify leading lines in artworks, because the current framework necessitates the user to set this threshold by themselves. Also, the orientation of the gaze shift along the approximated leading lines remains unexamined, but we believe that it may be possible to estimate based on the corresponding area of the ridge cycle of the saliency map, or by utilizing vector field topology. And finally, we need to utilize multivariate computational topology techniques because they enable the analysis of relationships among various properties. Since our method is based on a saliency model that employs local low-level image features, content-based leading lines, such as those conveyed through people's gestures and facial expressions, cannot be captured. And some leading lines based on low-level image features such as brushstrokes also remains elusive. Thank you for watching.